This conference will now be recorded.
All right. Hello and welcome to SFPUG February Meetup. I'm your host, Catherine Saar. Before we begin, the meeting is being recorded and will be posted on YouTube afterwards. Everyone who speaks during today's event will be part of the recording. We will do the Q&A at the end of the presentation. If you choose to ask a question, your voice and image, if you have your camera on when speaking, will be part of the recording. If you do not ask a question, you will not be part of the recording. If you're using the most recent version of the app, which we do recommend, you can use the raise hand function to join the queue. If you're using an older version of the app, which does not have this function, please use the chat to let organizers know that you would like to ask a question. They will add you to the queue. The organizer will let you know when you're next in the queue so you can be ready to unmute your microphone and ask your question. If you do not want to be a part of the recording, the organizers can convey your question to the speaker. In that case, please type out your question in full and let the organizers know you would like them to present it to the speaker. If you have any technical issues, please message the organizers for assistance. If you drop out of the meeting and are unable to rejoin, you can post a message on the event page on Meetup, which we're monitoring during the presentation. SFPUG, Bay Area Postgres, is a PGUS affiliated user, and I'm a volunteer for PGUS. SFPUG is sponsored by PGX, and I work for PGX. And without further ado, here is Christophe Pettus with Language as a Virus, Managing Locales in PostgreSQL.
Hello, let's get the screen share going. I think I need to be granted screen share permission again.
It looks like you still have it.
There we go.
Yeah.
Okay. Bonk.
Perfect.
All right. There we go. So thank you all for attending. I'm sorry for all the chrome around the slides, but GoToMeeting in full screen mode don't interact very well. I'm Christophe Pettus, and we're going to talk about well, first, I'm the CEO of PGX. We're a boutique Postgres consultancy based in Alameda, California. I've been doing databases for a long time. And I'm going to be here to talk about why language was a bad idea and probably shouldn't have been invented in the first place. Yeah, okay, just kidding about that. But handling natural language in computing is complicated, and we're going to talk about some of the complications. Okay, before we do anything else, we're going to talk about glyphs, and because this is a very basic thing, but getting this right is important to understand kind of everything else that's coming on. So a glyph per Wikipedia is any kind of purposeful mark, which is pretty generic. So in practice, these are glyphs, AZ for U with an umlaut. Those are glyphs too, looks like cartoon swearing. Pictographic languages and syllabic languages have glyphs too, and even emoji are glyphs. So unfortunately, computing being computing, they kind of got the terminology wrong right from the start. In linguistics, a glyph is distinguished from a grapheme, which is the glyph is the mark itself. So those are three different glyphs, even though they're all Latin lowercase a but just in different fonts. The grapheme is the underlying functional unit, which is to say those are all lowercase Latin b's. Unfortunately, we use glyph to mean grapheme, so we're going to use glyph too, and there's no changing this now, unfortunately. Now, we're computer people, and we're really, really familiar with the term character. So a glyph more or less corresponds to what programmers will call a character. There are some exceptions to that. One of them is called combining characters, because you look at an E with an umlaut, is that one or two glyphs? Is it an E glyph and an umlaut glyph, or an E with an umlaut glyph? And actually, there's disagreement on this point, and you can start fights with this question. Unicode supports both, which is a pain in the neck, and fortunately beyond the scope of this talk. If you want a whole talk about Unicode sometime. It's almost safe, though, to use terms interchangeably, so we'll do that too. We'll generally use character because, this is not computers. Now, way back, really early, computer people said, well, okay, if we want computers to understand glyphs, well, or characters, we need to come up with numbers for them, because obviously there's no RAM out there that can store a letter A by itself, a literal letter A. So the terminology we're going to use is that the number that's assigned to a particular glyph is its code point. This is the term Unicode uses. And a complete set of code points for a particular set of characters, generally the characters necessary to write a particular language, is a character encoding. Now, for a long, long time, when you talked about a character encoding, you meant one thing, which is you meant ASCII, which stands for the American Standard Code for Information Interchange, in case anyone didn't know. It's been around a long time. It was kind of finally codified in what we're using today in 1967. It assigned a 7-bit code to the traditional Latin alphabet, to Arabic numerals, a few commonly used at the time symbols, and some control characters. For example, an uppercase A is hex 41, lowercase a is hex 61, and an asterisk is 2a. So that's easy. Very nice because, fits in a byte, which, 8-bit computers had pretty much dominated at that point, although there were 6-bit computers, which were interesting to map ASCII onto. And it was a pretty cool idea. Like, you could just capitalize a letter by adding hex 20 to it. And if you had a digit character, a digit 3, you subtract hex 30 from it, and now you have a byte with value 3. And for a long time, this was basically all we had. Well, okay, IBM, we also had EBCDIC, but we don't talk about EBCDIC. And this character encoding is now, when you talk about, people say 7-bit ASCII. Now, technically, that's redundant because ASCII proper is always 7 bits. ASCII doesn't use the high order bit on an 8-bit byte. But we need to distinguish because instantly ASCII was obsolete because it was designed to handle basically a teletype. An ASR 33, if anyone's that old. And there's no way of encoding a lot of characters commonly used in non-English languages, and in English for that matter. I mean, you run into diacritics of all kinds. And of course, if your language doesn't use the Latin alphabet, forget it. There are no non-Latin characters in it. So everyone immediately ran off and started developing their own encoding. Some just repurpose that high 8-bit to use for a bunch of different characters. Some use multi-byte characters. For example, Chinese writing, any of the Chinese writing systems, there are so many symbols you can't fit them all into a single byte. Often, sometimes not into 2 bytes. And this was chaotic. The Internet Association for Assigned the Internet Assigned Numbers Association, I forget how that acronym expands actually, documents 259 encodings, and there are plenty more. So the world is packed with them. So this was awful. And so there was an initiative to fix this problem, and the fix was called Unicode. The Unicode Consortium was formed with a bunch of different companies, and the first Unicode standard was published in 1991. And the goal is to assign a code point to every glyph used in human communication, which is pretty ambitious. Unicode code points run from 0 to basically that. It's not. Unicode uses U+ rather than to indicate a code point, so we'll try to do that also. Practically, because of internal structure and things like that, Unicode defines 2 to the 20th possible code points. 7-bit ASCII maps into Unicode with the first 3 bytes set to 0. So the very first 127 characters in Unicode are the same as in ASCII. The Unicode is divided into planes, which are basically the high order bits of the Unicode code point. And the one most people are interested in is called the basic multilingual plane, and that's basically the lower 16 bits. With the Tolkien reference above, I have to note that Tengwar is actually not formally a part of Unicode yet, although they've allocated code points to it. So Unicode a character encoding. Well, yes and no. It's a complicated question, actually. Unicode itself is extremely complicated. It has lots of structure, and we're not going to talk about all that. Now, it is a character encoding because it does map glyphs to code points. If you have a Latin lowercase a, there's a code point for it. But it doesn't specify how we store those inside the computer. So there's the easy way, of course. Unicode, takes 3 bytes to always represent a Unicode code point. So we could just make every character 24 bits or even 32 bits. Needless to say, no one was really excited about suddenly having their character strings be 4 times as long. So a different solution was called for. And that different solution was called the Unicode transform formats. So if you ever wonder what the UTF and UTF-8 stands for, that's what it does. This was a clever way of mapping a, let's call it 24-bit or 20-bit Unicode code point into a byte stream in a way that was packed the characters down in a reasonably optimal fashion. So what this means is characters are variable length. The easy part is if it's a 7-bit ASCII character, it's just like it was in ASCII good old-fashioned ASCII strings. So UTF-8 is a superset of 7-bit ASCII. To turn a 7-bit ASCII string into a UTF-8 string, you just say that's a UTF-8 string now, and you're done. That's really nice. Just a quick note on how UTF-8 works. You walk along the character string, and if the byte's less than hex 80, it's 7-bit ASCII. Then if it's not, if that high order bit is set, it's translated into a 2 or 4 byte. You read the next 2 to that byte plus the next 1 to 3 bytes, so a 2 to 4 byte sequence, and you come up with the code point. I'm not going to go into the rules on how that's transformed. You can look them up. But for example, Unicode E with an umlaut or diacritic there is hex 8 E9 in Unicode, and it maps to C3 followed by AB. And the rooster emoji is hex 1F413, and it maps to those 4 characters. 4. So you have one character could be from 1 to 4 bytes long, which breaks strcomp, the string comparison function in C. Because let's compare like uppercase Z and E. So if we just drop them into string comp and say do it, it says, well, Z comes first because it's a 5A, and then E with diacritic is C3, and that's bigger. And that's wrong for every language that uses the Latin alphabet. I'm sure I'm missing one where Z actually is lower, but you get the point. And the comparison, if you do this comparison, it becomes out of sync because now the character after that Z is being compared to the AB, which is still part of the E with the umlaut, and bad things happen. Because number of bytes is not equal to the number of characters. And the result is we're kind of still struggling with UTF-8. There are decades of code assume that one character equaled 1 byte, and the code reading UTF-8 needs to know that it's UTF-8 to display it properly. If you've ever seen that comma blah 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 on a web page where a quotation mark should be, that's what happens when you don't know it's UTF-8 and you're trying to interpret it as ASCII. So how do we sort things in the right order? Now we're getting to the fun part, which is collations. A collation is just a function. In its simplest sense, it takes 2 strings and returns and compares them and returns if it's greater than, less than, or equal to. That's it. This is the basis for sorting character strings. There are lots of collations out there. Each collation is specific to a particular character encoding, because obviously you need to decode the bytes to decide what you're going to do. But an encoding can have lots of different collations. On my laptop, there are 53 different collations just for UTF-8. So there are lots of collations out there, not just sort by the bytes. And a collation is generally specific to a particular natural language. But natural languages can have more than one collation. Like German sorts names as they appear in a phone book differently from words in a dictionary. And Danish has a different collation for continental Danish and Greenlandic Danish. So And languages also have different ways of formatting numbers. Countries write dates differently. There's all sorts of stuff that's like localized. And so eventually we came up with a way of bundling all this stuff up, a collation, how you format stuff, things like that, into a single bundle. And we call that bundle a locale. So that's what a locale is. It's just a bunch of code and supporting data, and it's a bunch of utility functions that handle different language and region-specific formatting, like number formats, character encoding, and like some utility functions related to the character encoding, like how to capitalize and lowercase characters, if that's appropriate for the language. Date and time, the string collation to use, currency format, all sorts of things. So we're interested in the character coding of the string collation part. So on pretty much any Unix-derived system, the collation system that comes with it is called POSIX locales. So pretty much everybody, and Windows has locales also, which are confusingly similar. They have different naming conventions and things like that, unfortunately, but there they are. And the name of it, so there's a bunch of locales that come installed, and you can install more with different packages on a Linux system, Unix system of any kind. And they're given names, and everyone's probably seen the one that's, US underscore uppercase US.UTF-8. So that's kind of the common name for it. The first two letters are the language, so that's French, FR is French. The next one is the region, so uppercase BE is Belgium, and UTF-8 is the character encoding. Often they drop the UTF-8 part or the part after the period if there's only one locale for if that combination of region and language only has one character encoding. There's also a big exception to the rules, which is locale that's either called the C or POSIX locale, or sometimes the C/POSIX locale. It compares, it takes the string as it finds it, as the C language used to, just a string of bytes with a null byte at the end. And it's really fast because just basic byte comparison, but of course it's not going to work for for anything with non-7-bit ASCII characters, which are usually UTF-8 or UTF-16. It can even break for equality. You can represent E with the dots above it in two different ways in Unicode, either as one glyph or two, and that suddenly those are not even equal to each other. So use this with caution. We'll talk about use cases for particular locales in a little bit. Okay, so locales come bundled together in big libraries, which is called a locale provider. On Unix systems, POSIX locales are provided by the library libc, the runtime that implements most of the underlying runtime system for the C language. On pretty much any system you're going to run into, any Linux system or open source systems, this is usually the GNU project version of it, glibc. In fact, that's so common, they're often just called glibc locales. They don't talk about the POSIX part. There are other locale providers, like the International Components for Unicode, ICU. And in version 17, PostgreSQL has its own built-in locale provider. And we'll talk about why you would use those two alternatives. So a little bit about International Components for Unicode, or ICU. It's a large, big old library of utility functions for Unicode. And it includes a staggering number of locales. It even has a build your own locale system. For example, you can build locales like that long string, which means it's US English and sort numbers as a single number. So 1, 2 will 1, 2, 3 will sort after 1, 1, which it would not if you were doing just byte comparisons. And it's case insensitive. That's what all of that means there. And since version 10, PostgreSQL has supported ICU as a locale provider. In fact, ICU has this secret weapon, which is a collation, which has the unfortunate name of UND-X-ICU. And what this is a good enough collation for the whole Unicode space. It's not guaranteed to be correct for any particular language. sometimes it is, sometimes it isn't, depending on the language. But for any kind of non-specialized use, you're not generating a German phone book or something like that, it's good enough. And this will be very helpful to have a collation like that, which we'll talk about in a bit. Okay, so let's talk about locales in PostgreSQL, finally. So databases need to know about locales because they use the kind of functions that come with locales all over the place. They use them in string comparison, building indexes, output functions, all sorts of stuff. And when you create a new database in PostgreSQL, you specify what locale should apply to it. Some of the things that you specify in a locale you can change on a table by table basis, but you can't change the character encoding once the database is created. When you create the database, you have to pick what character encoding it's going to use forever and always. So that means you should use UTF-8. There is really no other reason to use any other character encoding at this point, and using the other possible character encodings will just get you into trouble. Okay. Like everything, there are some exceptions. If you know for sure your database will never accept any natural languages data, it's always going to be symbols or codes for things, and the bottleneck in the database is going to be string comparison, then you might pick POSIX locale instead. These probably do not apply to your database though. Especially the second one. Very rarely is string comparison going to be the bottleneck in a database. So just use UTF-8. Your life will be so much simpler. And the reason I am warning you against using C encoding is that C encoding will happily accept any non-7-bit ASCII. It's bytes. Bytes is bytes. It does nothing to interpret them. When it compares them, it just uses strcomp. This means you could end up with mixed encoding in a single table. You cannot guarantee that a web client, for example, is going to send you UTF-8. It'll send you whatever it's configured as, which is probably something exotic. Postgres is able to convert a lot of these to UTF-8, and so that solves the problem. But if it's C locale, it'll just slam it into the database, and you end up with a database with mixed encodings in them. This is really hard to fix. We've had to do it at PGX three times, and it's no fun. So really just don't use C encoding unless you know for sure it's what you need. One more thing. You may see someplace references to SQL _ ASCII encoding. Pretend it doesn't exist. It's causes no end of problems. It's horrible. Let's pretend we didn't even say that. Okay. Well, we've decided we're going to use UTF-8, but what locale should we use? And this is a little bit more complicated question. Pretty much any Linux distro will come pre-configured to be used en_us UTF-8. Okay, and that's not a bad choice, especially if it's an English language database, but there are other better choices. But before we get into why you should use different locales, let's talk about a disaster that happened within living memory. And this is when suddenly this is kind of what made everyone aware of locales in Postgres and what could happen. Okay. First, a little digression about an index. We all, database people, we know about indexes. But what is an index really? And in a sense, it's a cache. It's a cache of comparisons of the fields that form the index, because you could always do a sequential scan and do index stuff that way, but that's really expensive to have to recompute it as scan everything every time. So we build a cache and we call it an index, and we store it in a structure that's fast to retrieve, like a B tree. And like they say, the two hardest problems in computing are naming things, cache invalidation, and off by one errors. And that means sometimes an index can become invalid unexpectedly, and we call that index corruption. And sometimes detecting that is really hard. Because indexes on character strings depend on the collation function you're using, kind of obviously, you have to compare them. But what if the collation function changes? Suddenly the cache is invalid because the one that it's using now was not the one it used when it built the index. So you have to rebuild the index, but what if you didn't know the collation function had changed? You have a corrupted index. This all sounds very hypothetical, but it happened. When glibc 2.28 was released, it had this little note in the release release notes. Now you can read this, and when you read it, you probably don't think immediately, "Oh my God, my database is going to be corrupted," but that's what happened. Most of the non-C locale indexes with non-ASCII characters were affected, and it manifested as in PostgreSQL as index corruption. And this version is the one that shipped with a bunch of very common distributions. And there are several ways that you could upgrade to this version of glibc without really realizing you're doing it. For example, let's say you had an older version, an older OS as a primary, but a newer OS as a replica. It's sending over the binary data, so it's not reconverting, it's not re-indexing anything, but so it's effectively building a corrupt index on the other side. You upgraded the OS in place. This isn't as common as it used to be, but people still do it. You move the data directory to a different system. You detached it. In an environment where it's a NAS, you could detach it from one system, mount it on another, and that new one is a newer version of the OS. Or you're storing a binary snapshot, using pgback rest or anything, and but you're restoring it to a new system. It's the same architecture. It's the same, probably the same distribution. You're going from Ubuntu 16 to Ubuntu 18, and you think, what's the problem? Well, this is the problem. So the one question is, well, what if we use ICU as the locale provider? Will this fix this? Well, obviously, it wouldn't have had the glibc problem because it's not glibc. But ICU collations change too with new releases of ICU. Significantly less frequency than glibc changes. But this, just saying we'll use ICU does not completely fix the problem. So what do we do? As of version 10 for ICU and version 13 for glibc, if there's a mismatch between the collation function that was used to build things and the current system collation function, it'll issue a warning. In the case of glibc, it'll issue it anytime glibc gets upgraded because it doesn't know whether or not the specific collation functions upgraded. ICU gives a little more detail. These are emitted into the text log, so check your text logs. There's a lot of interesting stuff there. And if you see the warning, rebuild any indexes that are involved. And because you don't know whether or not you suddenly will start getting weird index corruption issues. Or you can use the built-in provider. In version 17, PostgreSQL has its own locale provider, which is guaranteed to never, ever, ever change, which is very nice. It's not as sophisticated for natural languages as ICU or even glibc, though. So you are making some trade-offs. It only has 2 collations in this locale provider. The C, which works by using strcomp, compares the strings just like it is. It produces really bad results for UTF-8, like we discussed here earlier. There's also the C.UTF-8, which basically compares the UTF-8 as the numeric code point. So you can think of it as it walks along the string. If it finds a Unicode character, it turns it into the full 16 or 30 or 20-bit, 24-bit character and compares that with the other. So any Unicode character that's not 7-bit ASCII will collate higher, later than 7-bit ASCII. So it's not correct for any natural language, but it doesn't have that falling out of sync problem, and it's less wacky than C collation, and it's fast. So basically, it still gets that Z less than E with a diacritic wrong, but UTF-8 gets it kind of less wrong. So at this point, you're thinking, do I really have to? I just want to run my database. What should I do? So here are some typical use cases for your database and what you might want to do. So, case 1, you want maximum speed. You're running on PostgreSQL 17 or higher, and I don't really care if the collation is wacky for non-7-bit ASCII characters. That's not an important thing. Use the UTF-8 locale from the built-in locale provider. Problem solved. You never have to worry about ICU or glibc changing out from under you, and it's fast. But let's say, okay, you haven't upgraded to 17 yet. and you're willing to swear that you will never put a character in the database that's not 7-bit ASCII somehow. I don't know how you make this promise, but let's say you do. Okay, now you have my permission to use the C PostgreSQL locale with the caveat of not putting 7-bit ASCII data into it, or non-7-bit ASCII data. You're willing to trade off a little bit of speed so that you have reasonable collations across languages, so you don't get angry complaints from people who are doing sortations on German names. Or you're on a version before 17 and you do want to use non-7-bit ASCII characters. Then use the ICU UNDX ICU locale. That will give you pretty good results for most Unicode characters, and it's supported before version 17. And so it's a very good compromise of speed versus linguistic functionality. Now you're building something, so the collation has to be absolutely correct for one particular language, but that will be the only language in my database. You know, you're working for an Italian company, and you want to make sure that all the Italian sortation works correctly, but you don't really care about anything else. So use the libc or ICU locale specific to your language requirements. You know, find the one that maps to the way you want strings to sort, and use that one. And you've upgraded 17. Congratulations, excellent idea. 17 is a great release, and you never ever have to want to worry about this nonsense of glibc being upgraded and breaking, corrupting indexes and things like that. Once again, just use the c.utf8 locale from your built-in locale provider. Done. Problem solved. We're going backwards to case 5. Oops, case 6. There we go. Case 7. Now, but you're on a version earlier than 17, and you never ever want to worry about the locale provider changing. Unfortunately, in that case, you're stuck using the C PostgreSQL locale, because in that circumstance, it's the only locale collation function that's guaranteed not to change, because it doesn't depend on any of the, there's no algorithmic change that we could ever have. If we change the algorithm that strcomp uses, we'd have bigger problems than, sorting last names. Okay. You need to use libc or ICU because you want, good linguistic sortation, or you want to take advantage of some of the nice features that ICU offers. But you're worried that they're going to ship a new version of libraries, things will break, horrible things will happen. So you can take some steps to mitigate this problem to the point that you really don't have to care about it very much. So first of all, upgrade to PostgreSQL 17. Never ever run a primary and a binary replica on two different versions of the OS. So never restore a binary snapshot onto a different version of the OS. And if something changes and you get the warning that there's a mismatch, what you want to do is race over, if you're using ICU, or you issue an alter collation refresh version command that tells it update to the latest version of the library and reindex your database. Fortunately, this doesn't happen very often. This is not something that happens on every release, but if you move to a new OS and are using the same binary image of your database, that's when you have to worry the most. Or you fire up a new replica and it's a newer version of your particular distribution. Just as a note, if you want to use ICU, which I recommend, there's a couple of extra steps involved. You have to create a collation object inside of Postgres that where you take that kind of weird, the ICU format collation and give it a name inside of Postgres, and then you use that name to specify the collation, for example, on a table. You can also use ICU as a version 15 when you create the database. You can specify an ICU locale, so you don't have to worry, add it to every single table. In this case, you do use the ICU format name. One thing that can be a surprise is because you can't change the character encoding on a Postgres database once it's created, you have to use template 0, because template 1 does have a character coding associated with it. It'll just give you an error. So you have to specify template 0 if you're creating something with a locale other than what template one was created with when your database was installed, when Postgres was installed. Okay, so how fast or slow is all of this? I mean, I've sort of waved my hands and said, this is faster, or this is slower. So I tried an experiment. It's not exactly the most sophisticated experiment in the world, but it gives you an idea. So I created a table with 1 million large random strings and did a select from order by on my laptop. And I ran them a ton of times to get around, to mitigate, make sure caching was not an issue. The built-in provider using C.UTF-8, which is the one you should use if you're using the built-in provider, was basically the same speed as libc. That I would call that 16 millisecond difference in the noise margin of error for that. Going to my favorite collation, UND-X ICU, it was slower, but I would say that's still probably acceptable. Using the Austrian-German collation from ICU was basically the same speed as UND-X ICU, so that's great. And then libc was like really slow. Really, and this held true across multiple different locales from libc. So what did we conclude from all this? So locale stuff is hard, but it's manageable. It's generally you set it up and it kind of just works. The only exception to that is is when you have to do upgrades and things like that. Then you want to have a checklist and things like that. One thing I do recommend is make a conscious choice of what locale to use. Just don't take what the system throws at you. Think about your use case, because it's especially important when you're creating a new database, because you're going to live with that for the rest of the database and time, unless you want to do a dump or store. Not enough people are using ICU, in my opinion. It's very powerful. It's very fast, and it also changes less often than glibc. So consider using ICU locales. And the other thing is, if you think you're never going to get foreign language or non-7-bit ASCII characters in your database, you're probably wrong. Even if you think you're going to be American English only forever and always, people in America have E with an accent in their names, and all it takes is for them to type that in and submit it, and suddenly you're in 7-bit ASCII world, non-7-bit ASCII world. And thank you. That's the talk. Any questions?
Let's see.
Too overwhelmed. To ask the question that always comes up, these slides will be, I think it's on the, oh no, these will be posted on my personal blog, which is thebuild, all one word.com.
It looks like Rustam has a question.
Hi there.
Rustam, did you have a question? Or maybe not.
Totally overwhelmed with the torrent of information.
There was a lot of info. All right, anybody else? Any questions or comments? Okay, well, that was a great talk with a lot of information in there. Oh, he says he's having issues with his mic. Rustam, if you want, you can just type in your question, and I can relay it to Christophe. Okay, there we go. How can I enforce 7-bit ASCII in my database? Perhaps some sort of constraints can be applied.
You could write a trigger function for, constraint trigger, for example, that looks at the string, takes it apart, it's just data, and throws an exception if, kicks it out with an error if it's not 7-bit ASCII. You could do it from the application point of view, but of course that means the application has to always moderate between the import source and the underlying database. I will say my basic feeling is don't, except, because if, for example, you're using UTF-8 encoding, it will accept it, and then you deal with it. You just accept that as part of the application. Generally, the only databases that never ever have to deal with non-7-bit ASCII are ones that don't really use natural language in the sense that people are typing their names or it's storing text. Is that the only text in it are things like codes, or for enumerations and things like that, where the only source of it is something that's hardwired into the application. Often these need to run very, very fast. Sometimes they're like real-time systems, and so every little microsecond counts. And then in that case, using C locale or something like that is reasonable. But yeah, that's my advice. But you could, if you really wanted to be diligent about it, you could in fact write a constraint trigger that looked for non-7-bit ASCII characters and rejected them.
And he says, thank you. All right, is there any other questions or comments? Okay, then I think we will go ahead and wrap things up. Yeah.
Go to pgexperts.com and check.
Okay. Want to thank Christophe for a great talk. Thank you again. Thank you, PGUS and PGX. We do not have a speaker for March, but we will be back on Tuesday, April 8th for Where Do Performance Cliffs Come From with Thomas Vondra. Upcoming conferences are Scale 22 is March 6th through 9th in Pasadena, California. PG Day Chicago is April 25th, and PGConf Dev is May 13th through 16th in Montreal, Canada. We will send a link by email when the video is ready, and you can watch our social media. You can find us on LinkedIn, Mastodon, and Blue Sky by searching for Bay Area Postgres. We are looking for more speakers for 2025, so if you or someone you know is interested, please contact us. Thank you everyone for attending, and I hope you have a great rest of your day. Thanks so much.